Use the rational zeros theorem to find the zeros of p of x equals 2x to the fourth minus 9x cubed plus 6x squared plus 11x minus 6. Then use the zeros, the end behavior, and a few extra points to sketch its graph. All right, so we know by the rational zeros theorem that any rational zero will be in the form p over q, where p is a factor of the constant term, negative 6, and q is a factor of the leading coefficient, 2. So the factors of negative 6 are going to be 1, negative 1, 2, negative 2, 3, negative 3, 6, and negative 6. And the factors of q are 1, negative 1, 2, and negative 2. So effectively, to get all of the possible rational zeros, we can look at all of these numbers and divide them by either 1 or 2. We don't have to worry about the negatives because we have the negatives taken care of up there. So the list of possible zeros, if we divide all of these by 1, gives us 1, negative 1, 2, negative 2, 3, negative 3, 6, and negative 6. And if we divide them by 2, it gives us 1 half, negative 1 half. 2 halves and negative 2 halves we don't need to do that because we already have 1 and negative 1, which is what we get when we divide them by 2. And so then we've got 3 halves and negative 3 halves. And again, 6 halves and negative 6 halves are just 3 and negative 3, which we already have. So this is our list of potential rational zeros, which is much larger than the list we had for the last problem. And so we've got to go through trying these and hope that we have good luck and we find a rational zero quickly, so we're not guessing 12 times before we find something. So I'm going to start with 1, 2, and 3 because positive integers are the easiest ones to deal with. So we'll start with 1. Let's put in the coefficients. And let's go through with synthetic division. So drop down the 2. 1 times 2 is 2. When we add, we get negative 7. Times 1 is negative 7. We add, we get negative 1. Times 1 is negative 1. We add, we get 10. Times 1 is 10. We add, we get 4. And because this is not 0, it tells us that 1 is not a zero of this polynomial. So let's continue with 2. Of course, you can do these in any order you want, but who wants to start with fractions when you can start with integers? And who wants to deal with negatives when you can deal with positives? I will generally start with positive integers because usually it makes our life a little bit easier. So we bring down the 2. 2 times 2 is 4. We add to get negative 5. Negative 5 times 2 is negative 10. Adding gives us negative 4. We multiply by 2. That gives us negative 8. Adding gives us 3. 3 times 2 is 6. And here we do get 0. So that means that 2 is, in fact, a 0 of the polynomial. And so we can rewrite our polynomial now. We can rewrite our polynomial now. P of x equals x minus 2 times 2x to the fourth minus 5x to the third minus 4x squared plus 3. And now we can continue looking for more zeros, but at this point we can actually rule out 6 and negative 6 because now our leading coefficient is 3, and so we are no longer going to be considering 6 and negative 6 as zeros. By finding the first 0, this actually allows us to rule out more of them because we have a new constant term and leading coefficient. So we've done 1, we've done 2, let's try 3. So our new coefficients are 2, -5, -4, and 3. So we bring down the 2. 2 times 3 is 6. Adding gives us 1. 3 times 1 is 3. Adding gives us -1. 3 times -1 is -3. Adding gives us 0. And because we have a remainder of 0, we've found yet another 0 of our polynomial. So now we can write our polynomial as x minus 2, because 2 is a 0, and then x minus 3, because 3 is a 0, and then that leaves us with the coefficients here of 2x squared plus x minus 1. At this point, we have the remaining polynomial, the kind of the leftovers, at a point where we can factor, because it is a second degree trinomial. Now, I'm not actually going to take the time to do that because we've done that so many times, and I don't want this video to be too incredibly long. So at this point, when we use the AC method, we should end up with x plus 1 times 2x minus 1. And then this gives us, for zeros, 2, 3, -1, and 1/2. If you set 2x minus 1 equal to 0 and solve, you end up getting 1/2. So these are our zeros, and we can plot them on an xy plane. So we have 2, we have 3, we have -1, we have 1/2. We have a y-intercept of -6. So that tells us that in this interval from -1 to 1/2, we're going to be below the x-axis. To figure out what's going on the next interval, we need to pick a point between 1/2 and 2, an x value between 1/2 and 2. We can pick 1, but the beautiful thing is that we've already done the work here, and we know from the remainder theorem that p of 1 is going to be equal to 4. So that gives us another point, and that tells us that we're going to be above the x-axis here. So now to figure out what's going on between 2 and 3, we need one more point. So we can do 2.5. And if we do that, let's see, 2, -9, 6, 11, -6. So we get a calculator because that's going to make our lives much easier. We bring down the 2. 2 times 2.5 is 5. Then we subtract 9 to get -4. Then when we multiply that by 2.5, we get -10. -10 plus 6 is also -4. When we multiply that by 2.5, we get -10 again. 11 minus 10 is 1. 1 times 2.5 is 2.5. And 2.5 minus 6 is -3.5. So we've got the point 2.5, comma, -3.5, which is right there. So we're going to end up being below, above, and below. And for the end behavior, because this is a fourth degree polynomial with positive leading coefficient, we're moving up in each direction. So we're going to end up with a graph that looks something like this. And again, moving up in each direction for our end behavior. So this is a sketch of the graph p of x equals 2x to the fourth minus 9x cubed plus 6x squared plus 11x minus 6. It is accurate as far as the x and y intercepts go. Also, the intervals where we're above and below the x-axis, as well as the end behavior. But again, we need calculus to find the local minimum and maximum values.